field.
Okay. Started.
Okay, so I think I will start. So hello, everybody. This is the last lecture. And I want to start by a solution to one exercise which I've been actually using. And that will be the only exercise part of today's lecture, because there is well, it's the last lecture, so I want to more or less to tell everything I have in mind. Okay, so the exercise is to show that if you take a type and pick an element of this type, so you suppose that it is inhabited, then it is always the case that this type here is contractible. So the type which has as inhabitants a pair of an element of A and a proof that A is equal to X. And this type is contractible. So how do we prove this? Well, first we need to find a center. So, but we already have a chosen inhabitant in A, so we could pick him, and then we just need to find a proof that A equals A, and we take the reflexivity. So that's very easy. And then what we need to prove is that we have a, if I take an arbitrary element in this type, so of the form XP, I need to find a path from it to my chosen center. Okay. So we need to provide a proof of this equality, okay? But by the analysis of equality in sigma types, we need to prove that A equal to X, but this is exactly what P is saying. XP being an inhabitant of this type, it just means that X is in A and P is a proof of A equals X. So this P is a perfect equality between A and X. And then we have to see that P and ref A are the same up to this up to the transport, okay? But the transport, we have seen already this this equation for transport. When the type family has this shape, then transport is just a concatenation. So transporting along P, the element refle, which is here, is just concatenating with P, but by the laws of the monoid laws of path concatenation, this is the same as P. Okay, and this is all propositional, but this is exactly what we want. So end of exercise. And now, no, sorry, now I want to switch to another, yes, okay. And now I want to give the plan of the lecture, okay? So yesterday I stopped at the beginning of the proof of this property here, so I will try to finish it. This property is to show that function extensionality is a consequence of univalence. I prefer to say it in a more precise way. It's a consequence of univalence and of the Eta rule, which is a kind of weak notion of extensionality. And then once this is done, we really arrive to the last part of the course. So the last part of the course will be mainly concerned with things like the sphere, and some other topological constructions which are very well known, the loop spaces, suspensions of spaces, and then something called fiber sequences. Okay, but before doing that, okay, before studying the circle, and for the circle, we will establish this very well-known result. So if some of you have taken or will take a course in topology, in algebraic topology, one of the first results that they will meet is that the fundamental group of the circle is also called the one sphere, is isomorphic to Z. Okay. In order to prove it, so we need some tools. And one of the tools we need is something called the decode-encode method, which I will introduce before. So before speaking about topology, I will still remain in type theory, and I will try to show you the idea of this method and how it works for another problem, which is to characterize the equality in the coproduct type, again in terms of equality in A and equality in B. So it's in the same spirit as what we've done for the sigma types, for example. Okay, so we will introduce this decode encode method. It will be very useful in the proof of this. Then, of course, I will need to introduce type theoretically what are the integers, because so far we have only seen the natural numbers. And at some point in the proof, we will also need to know that Z is a set. And actually, the fact that Z is a set relies on the fact that N is a set. And again, if we want to prove this, so I will not do it in the course. It's one of the exercises. I think it's exercise number 16. But if you want to prove it, actually, you will also need the decode encode method to prove it. And the proof is actually very, very similar to the proof of what happens here. Well, because you know N is basically a recursive coproduct. So you of course you know that NAT is 1 plus NAT. It obeys this equation. So you see that there is a clear connection between NAT and coproduct. Okay, and so the decode encode method is used actually in the study of the fundamental group of the one sphere or the circle. It will be used twice. Once implicitly for establishing these properties that Z is a set, and one explicitly in the course of proving this equivalence here. Okay, and that's a plan. Okay, so let's carry on. Okay, so we were at the point of discussing that function extensionality can be deduced from univalence and Eta Rule. And I will not repeat this slide. In this slide, I sort of reduced the problem of showing this to two subtasks. Okay, one subtask is to prove that this type here, okay, so we clearly have fixed F here. Okay, and if we take the type of all pairs of G and prove that G is homotopic to F, is a retract of some other type, okay, which is this one. And so that was property 1. And property 2 is to prove the closure of contractible types under products without using functional extensionality, but using univalence. So I will sketch only the 1 because it's not difficult, and I will concentrate on the 2. So next slide is about the 1. Okay, so I repeated the 1 here in the title of the slide. So we want to prove this. And in order to prove it, actually, we prove a more general statement. Namely, we take one type family depending on A, and then a type family depending both on A and P. Okay, so we have two levels of dependency, and the statement is that this type here is a retract of this type here. So maybe I don't give too much details. You can see that our statement is just the instance of, so if we prove this statement, if we instantiate it with the type family indexed by x and y, which is f of x equal y, okay, qxy is f of x equal y, you can check by yourself that this is exactly the statement we want to prove. And in order to prove it, we need to exhibit yes, we need to exhibit a retraction. So you have to remember that a retraction is somehow half of a quasi-inverse. So we need to provide functions from here to here and from here to here, and we just need to check that that one is that one of the two inversions. So we need to check in this case that psi of phi of blah blah is blah blah. Okay, and well, I'm not going to comment this because I don't want to risk not having time for more important stuff. But it's really easy. The definition of phi and psi is a sort of forced upon you by the data you have. So you have data here, and you repackage them in order to get data here, and the same. There is strictly no difficulty at all. Okay, so this is sort of formal. So the second part, okay, so what was 2? 2 is a closure of contractible types under product. Okay. Okay, so here's a plan for the proof. We shall show, so this is our assumption. We have a family of contractible types. So each px is contractible. And we would like to show in the end that px is a contractible. So the plan is as follows. First of all, among the things that we have already showed and used is the fact that for any type family that has this property, then the sigma type here reduces to A. So you have an equivalence. The projection is actually an equivalence because all of these px are essentially singletons. So what counts is the first element of the pair. The second doesn't have any interesting information, except that it exists. So you have exactly, morally speaking, as many elements here as here, and you have an equivalence. So we've done this. So now we shall prove the following two properties. First, so I'm considering this map. So this map is important because I will use it in this slide and in the next slides. So I'm taking a map. Okay, so it's a map based on PR1, but the type now is A arrow sigma x px into A arrow A. And it's obtained by this lambda term. So you take a function here, you take an x here, and you precompose f with PR1. You put PR1 in front. So fx gets you to here, and then you do PR1, so you get here. So it is a way to say, well, if I want to say it in a more pedantic way, this is the way to say that A arrow blah is a functor, okay, a covariant functor. So yes, exactly. Okay, so but let's not use categorical vocabulary. So we want to we want to show two things about this alpha. The second thing is that alpha is an equivalence, given that PR1 is an equivalence. Okay, and the first property A is that the thing that we are interested in, so namely this type, happens to be a retract of this type here, the type fib alpha of id A. Okay, so suppose we have proved the two things. Then we can conclude, because alpha being an equivalence means that alpha is satisfies the predicate is a contremap. Okay, so it's the characterization of equivalence in terms of fibers, saying that all fibers are contractible. So since alpha, if B holds, then in particular the fiber at id A of alpha is contractible. Hence, now we know that by A, we know that this type here is a retract of a contractible type, and we have proved before that a retract of a contractible type is contractible. Okay, and of course, all this relies on you and me being confident that all the results that I'm using and calling do not use function extensionality, because otherwise the proof would be circular. So please believe me, and I also please to myself to believe myself. Okay, so then we know that we are reduced to prove these two things. So let's do. So proof of A. So now I've become more experimented with slide production, and I found one nice package that allows me to recall the statement. So I started to use it. So the statement I want to prove is recalled here. Okay, so usual business. If we want to show that something is a retract of another thing, we need to define two maps. Okay, that go in the opposite directions. And the one map is quite obvious. Okay, because you can go. Yes, you have an F here, and you want to go to the fiber of alpha, so you need to find a function in the fiber of alpha. Sorry, you need to find what is alpha. Yeah, you need to find a function here. Okay. Yes, in the fiber of alpha, you need to find an element of the domain of alpha, which is this one. So you need to find a function, and this function must map X to a pair. So you can type check that this is the obvious choice, and that ref is also the obvious choice. So let's not spend too much time on this. And then for psi, you will fib alpha will, I don't think I want to detail it either. Essentially, I would say that everybody can figure it by himself. Knowing that you start from this type here and you want to reach this type, you try to assemble things in a way that type checks, and then you arrive to this. Okay, and here I gave some indications of why type checks, and then we have to show that only that psi of phi of f is equal to f. Okay, so this we could do. This we can at least do. So it's psi of phi of f. So I reproduce phi of f here. And then psi, if I instantiate this psi with this and with this, I will get this formula here. Okay. Well, it reduces to this formula thanks to these simplifications which are here, which I don't want to detail. And transporting by reflexivity is also cancelling. So in the end, I have lambda x fx. And here there is something missing in the slide because the line is too long, but you arrive to f, and you arrive to f thanks to, well, here I prefer to use L equal. You arrive to F thanks to eta. Okay. So here I want to make some kind of philosophical point. The Eta rule, I always prefer that, well, if I'm in the setting of type theory, I really prefer to see it as propositional rather than definitional. First, because it is a consequence. Propositionally, it is a consequence of function extensionality. So it's, as I said, it's a kind of weak form of function extensionality. And the other reason is that, well, in the literature on lambda calculus, there are lots of papers speaking about eta, and they are divided in two stacks of papers. The papers who speak about eta reduction and the paper which speak about eta expansion. And both are interesting. So eta reduction is quite intuitive because F is clearly simpler text than lambda x fx. So from the point of view of reduction, rewriting, this orientation is rather obvious. But actually, eta expansion is much more relevant when you consider conversions of types in general. So I will not comment more on this. But just to tell you that since the world is divided and about the orientation of this rule, for me it's better to let everybody agree and to have a propositional equality rather than trying to orient it. Okay, good. Second thing to prove, the fact that alpha is an equivalence. Okay. Actually, it has nothing to do with this particular alpha. Okay. It is the statement is that for each, if as soon as you know that some E is an equivalence, then the map induced on for any type capital X, the map induced on the arrow type X arrow R to the arrow type X arrow B by this lambda term, okay, is also an equivalence. And this is the place in this whole proof that univalence implies function extensionality. It is the unique place where we make use of univalence. So it's somehow it's a crucial step. Okay, and the proof is easy, by the way. So first of all, without using univalence, we will show that this property holds in the case that E is obtained from some proof of equality of A equals B via the E to xv function. Recall that the E to xv function is there anyway. It's inverse that is postulated by univalence. So B1 should be rather easy. Okay, and then a second thing we will show, and this is going to be very easy because it's a business of transport. Okay, it's why it's so nice to have a propositional equality. So the property B2 says that if E1 and E2 are equal, okay, in their function type, and if this function induced by E1 happens to be an equivalence, then it is the case that the other one is an equivalence. Okay, so suppose we have proved B1 and B2. Let me show you that we have finished. So it's obvious. Now we use univalence here. Okay, so this is the place. So we have to prove the statement for all E. Okay, but so I take an arbitrary E, but I know that E is equal to E to XV of UA of E, okay, by univalence. Hence, I can use B1 to get my result for this guy, which I could call the E1 if you want. Okay, so I know it for E1. And by B2, if I now call E2, I know it also for E2. And that's end of the story, okay, because this is what I wanted. I wanted to know it for E, which is E2 according to B2. Okay, so let's now prove B1 and B2. Okay, so here I recall B1, I recall B2. So B1 is to prove the property B in the case that I have an equivalence coming from from an equality. So I have an E to X V of P. In this case, I have access to path induction, so I can reduce this to the proof where P, to the case where P is ref, okay. But we know by definition that E to X of ref does nothing, or is the identity functions, hence disappears. And we find ourselves faced with lambda fx, which is again lambda ff. And again, I have used eta conversion here. So here there's an eta. Okay, here there was an eta. Where was the eta? Ah, yes, it was here. So you see, eta is needed all the way, which is a good sanity check, because after all, extensionality cannot come from the void. It comes from eta and univalence, really. Okay, B2 now is even easier. Well, there's almost nothing to say. We just have to find the good family. So we take the family P from A arrow B to U, okay, defined by PE as exactly the thing that we wish, that is this type, is a key of lambda fx E fx, okay, and we take a path from E1 to E2, because this is the assumption of B2, okay, and then the second assumption of B2 is that we have an element in this type, okay, and we can just transport it by P, okay. Yes, transport P turns proofs of this statement to proofs of this statement, because this is a fiber at E1 and this is a fiber at E2, and transport precisely brings me in this type. Okay, so end of the story. So we have proved extensionality from function extensionality from univalence and eta. Okay, so next step in today's lecture, the study of equality in the coproduct type, with the aim of introducing introducing a method that will be used in other circumstances, the so-called encode decode method. So what is the statement we want to prove? Well, we want essentially to characterize when two elements of A plus B are equal, and here are common sense things that we would like to prove. So we would like to prove that in left of A1 is equal to in left of A2, if and only if A1 is equal to A2, in right the same thing, and in left and in right cannot be equal. Okay, that's a common sense thing. And that now the type theoretical way to say this is that because these are types, okay, the propositional equality is type. So we can phrase this in a rigorous type theoretical way by saying that this type is equivalent to this type. This is for all A1, A2, and similarly for the three others. And now, so theorem, this holds. But how do we prove it? Okay, so the thing is that it is not easy to prove this because too many things are fixed somehow here. No, it's not exactly what I want to say. Okay. One thing one thing that is makes things not easy here is that it's hard to think of using path induction right away because none of these guys are variables. They are already terms of some specific shape. They have a constructor in front. And path induction doesn't know how to handle these things. So somehow we have to reformulate the problem so that we will be able to use path induction at some stage. Okay, so that's one motivation. And then let's see what we shall do. So we shall exactly try to find a type or a family of type where something becomes a variable. And this is exactly what we are doing here. So we are defining a family, which we will call code, okay, which depends on A plus B. So it's a family code from A plus B to U, which is defined in a certain way, which I will comment. But the theorem is that this family will be shown to be equivalent to this other family, which is the one which is underlying all this part of the equivalences. So this type is this type family has a good shape in order to do some path induction because it's the family lambda z dot in left A1 equals Z, and you see that Z is variable. So we could hope to do some path induction based on fixing this guy. You can always, well, if you fix this guy, it's not a problem that it has a shape in left A1. But the problem is that if both have a shape in left, then I'm not in a good position. So, okay, so this is the motivation. And now how do we define code Z? Well, because this type is essentially accounting for this part here, of course, the code Z will account for this part. So code Z, code is a function from A plus B to U, and by induction on the coproduct, it's defined provided I can, as soon as I can define what is code of an in left of A and what is code of an in right of B. So if it's an in left of A, then I will define it as A1 equals A, because this is exactly what I read here, okay, replacing A2 by A. And if it is an in right, okay, I will define code to be 0 because this is exactly what I find here when I have an in right, okay? Because code is tailored to prove these two equivalences here, okay? But then, of course, we can make a symmetric version, or yes, a symmetric version that will prove these two. So we will prove, we will need to prove somehow this equivalence twice, because each of our methods deals only with two. Okay. Okay, so this is the definition of code. I'm sorry, this is the definition of code, and this is our goal. So let's let's go. Okay, so here's I recall the definition of code, and so I need to prove this equivalence here. So I need to define two functions in the two directions. Okay, so this is where I give names to these functions: encode because it goes to the code, and decode because it starts from the code. So encode, and encode is parametric in Z. So see, it is encode Z that goes to code Z, and this is decode Z that starts from code Z. Okay, so encode is easy to define by transport. Okay, so let's see that. Z is an element of A plus B. P is a proof that in left A1 is equal to Z. Okay, so we seek an element of code Z. Okay, yes. Okay, but. Okay, yes, and P. What was P? Ah, P is a proof. Okay, maybe I write it. P is a proof that in what? P lives here. P is here. P lives here. Okay, so the idea is, well, we want to go to get to code Z, and we transport with respect to code. So the idea is that we want to transport some person who is in code of in left A1. Okay, so we want to find somebody who is in code of in left A1. But what is code of in left A1? Here it's written. Code of in left A1 is the type A1 equals A1, and ref A1 is a very nice element in this type. So you see that this gives a correctly typed definition that goes in the correct type, and that is a very sensible way to define encode. So end of the story. There's no induction involved in this definition except implicitly in the definition of transport. So decode will be defined by induction on the sum type. Okay, so we will need to define decode on in left, and we need to define decode on in right. Okay, so I have to explain these two right-hand sides. Okay, so let's see what is the type of, what is the expected type of decode of in left A. Okay, so here it's the expected type of here, maybe I write. It's a code of in left A. Okay, but code of in left A can be replaced by A1 equals A. So let me replace it immediately. Okay, into in left A1 equals, remember that Z is in left A, equal in left A. And this is very easy because it's enough to apply the function in left. So I have a path here, and the function in left considered as a functor gives me a path from in left A1 to in left A. So this explains this code here. And in the case in right B, what I have to do is, so let me erase. In the case in right B, I need to find a function from code of in right B, but that's 0. So I need to find a function from 0 to whatever, Well, no, not whatever. Let's write it. To in left to in left A1 equals in right B. Okay. So in left A1 equals in right B. Okay, but we know the induction on the 0 type provides me with such a function. Okay, remember the discourse that 0 is like absurdum, and from the absurdum you deduce everything everything you like, or if you prefer the categorical language, 0 is an initial object. So you always have a morphism from 0 to any other morphism, a unique one. But here I'm just care about finding one. Okay, good. So this definition type checks. And what we need to do now is to show that encode and decode are inverses. Okay. So this is the last slide for the A plus B. Okay, so here I tried to recall all what I need. And let's try to read the slide. So, okay, so we want to show decode of encode. So we want to show decode of encode, decode Z of encode Z. The P of P is equal to P. Okay, so maybe I write this step first. Encode Z P. Okay, but if I expand the definition of encode ZP, I have exactly this here. Okay, so this is our goal. So now I can erase this. Okay, and this is our goal. Our goal is here. Okay, so here we can use a path induction. Well, apparently it's a based path induction. Yes, because my P has a fixed end. Yes, so it's a decode of encode ZP. Encode ZP. Okay, let's, yes. So we can take P to be the reflexivity. Yes, yes. The fix, apparently the point which is fixed is in left of A1. So we can take P to be the reflexivity, and then, well, we unfold the computation. So we instantiate P as ref of in left A1. So this again now instantiates to okay, sorry, yes, exactly. So P is ref and Z is in left. Okay, yes. So the fixed end was in left. So we now assume that P is a reflexivity, and hence, because P is between in left 1 and Z, Z is in left 1, in left A1. So we instantiate Z with in left A1, and what else? And we instantiate P with ref. So, okay, so with this instantiation of Z and this instantiation of P, we need to, this is done here, okay? And in the end, we need to get P, which is ref of in left A1. So I need to explain this. But this is easy, okay, because transporting reflexivity, transporting along reflexivity is the same thing as the identity. So this disappears. Okay, well, this is the identity function. Since it is applied to ref A1, what remains is ref A1. And then I have to compute decode of in left A1, ref A1. And here I use the definition of decode on something of the form in left. So I get up in left of ref A1. And application of reflexivity gives reflexivity. So I get what I want. For the other way around, we need to prove that encode of Z of decode of ZU is equal to U for all U. Okay, but we shall actually use induction on Z. Okay, so induction on Z means an induction on the co-product. Yes, okay, so there are two cases on Z. Either it's an in-right or it's an in-left. If it's an in-right, then believe me, it's going to be done by induction on 0, exactly in the same style we defined earlier the decode function in the case in-right. So this case is trivial by induction on 0. And if Z is in left, then the U here, by definition, this U is of type code of Z. Okay, it's a type code of Z, but code of, if Z is in left A, code of in left A was this equality type here. Okay, so we know, so okay, this equality type here, I'm not cheating, it's here, the same. So we, in this case, we have that our U is of this type. And what? Okay, and then we have to see what is encode Z, decode ZU in this case. So if I unroll the definition of encode, I have a transport code blah blah. Okay. Yes, I just where is this U up in left U? Yeah. Where is this? Ah, yes. Okay. Sorry. First decode ZU. Okay. First decode ZU, because Z is an in left A. Decode ZU is up in left. Okay. So this decode ZU becomes up in left U. Okay. And then an unfold the definition of encode, which is transport. Okay. Now this guy is actually up in left U, so it takes this place here, and then ref A1. Okay, so this is just by instantiation of the definitions, and now we have to work on this. Okay, so here we use a property of transport. I think, I don't know if I listed it among the properties, but it's quite intuitive. You see that if you have here there's a functor here in left, and here you have a type family, so you can compose the type family with the functor. Okay, so that's code composed with in left, and then this disappears. So you have this equation on transport, which says that transport code of up in left U is the same thing as transport relative to code composed with the function in left applied to U. Okay, this is also an easy property of transport. So it concerns this and this. Okay, the rest is not changed. So now we are left with this guy. Okay, but transporting reflexivity okay, so now we should remember that code. Okay, code composed with in left. What is it? What is it? It's just this special type family that maps Z to the equality type A1 equals Z. Okay, because this is the definition of code. Okay, should I recall it? Yes, code is here. Code composed with in left is just the equality type. So this type is familiar. Okay, it's this type family, and for this type family, we know how to define transport in terms of concatenation. So hence the transport here is just the concatenation of these two guys. So ref A1 dot U, and then by the unit law, I get U, and the proof is over. Okay, so this was the encode decode method applied to the co-product type. Okay, so now I have a proposition to make, which is to do the break now. Okay, it's a bit early, but it is the right point to make the break because all the rest of the lecture will be about mathematics somehow, about circles, loop spaces, etc. So it's a different world, and even if it's 1 hour, a bit less than 1 hour, let's start again at 3, and then you have to take your courage, and we will have 2 hours to do some math. Okay, so if you agree, we do like this.